detecting the change in magnetic flux. Are there other ways to detect vehicles? These magnetic sensors, obviously, you can also use for detecting trains, aeroplanes on the runway. So every big amount of ferromagnetic material is easily detected.
Isn't the natural magnetic flux of the magnetic field of the Earth is like the black one, yes?
It's like the black one.
And what happens with the red one?
The red one, so due to the attendance of the car, so the magnetic field will take the easiest way from one end to the other. So, so you can also talk about magnetic resistivity. And the magnetic resistivity of a car, since it's made out of iron, is very low compared to the magnetic resistivity of air. So that means that the magnetic field line will take the easier way, and the easier way will go over the car. That means that the magnetic field lines in the nearby environment will be drawn to the car. And under the car it's taken the normal way again. Yeah?
So we detect this point. We detect this point.
It will get focused into the car, and that means that the flux density in the car and obviously quite under the car will be increased. But that's the idea.
And if it didn't happen, we have matter with the loop detection or not?
With loop detection, if you cannot be detected, except you have a couple of iron pieces in your
like in the airport.
Like in the airport, yeah. So only metals can be detected. Yeah.
Because of the magnetic field.
Because of the magnetic field.
And what
the
about
crucial point is the magnetic permeability. So every material with a permeability constants unequal to 1 can be detected. And the higher the better. Because if it gets higher, then the magnetic resistivity will be lower, and so you can easily focus the magnetic field line.
What's the permeability of our body?
It's nearly 1.
This one.
It's more or less the same like air.
So this loop doesn't detect us if we pass through the...
No. That's why you cannot open the gate to a garage with your body. You have to have some metal things with you. But the human body can be detected very easily with a capacitive sensor. Because the human body consists 80% out of water, and water has a high dielectricity constant. So it's around 80. That means you change, let's say, a capacitive sensor. Maybe one electrode is the ground electrode, and one is the top electrode, maybe under the doorway. Now a human is passing this doorway, and this is the capacitor. The capacitance is given by epsilon times A over D. It's the area of the plate. D is the distance. So it's the distance between these two plates. This plate 1, plate 2. And now, if we look for epsilon, it's epsilon 0 times epsilon r. And epsilon r of air is roughly 1.0114. And now if a human passes the gate, epsilon r is changed to roughly around 80. That means the capacitance will be increased and you can detect the human being. So with magnetic fields, no way. But with a capacitive sensor, it can be easily done. Yeah? So that's the main goal of Sensorics. You have to earn knowledge about what physical law can be used to design a sensor. Because that's the main thing in Sensorics, to find some physical law that can be used and to change some physical constants like the electricity constants or the permeability constants for the magnetic field. And to use this law to build a sensor. Because Sensorics is always to map a physical quality to an electric quality. So here for the capacitive sensor, what we are using is the changes in epsilon r based on a human being. But it's rather an improved or more complicated sensor. There are more easily applied sensors than that. So we will not cover this example or the example with the anisotropic magnetic material. So other ways of detecting a vehicle. What
The
comes
weight.
to your mind? The weight. This would be another possibility. This is done on the highway very often. How is this working? So in our highway we got a scale, and if the lorry or the vehicle, whatever, is going onto that plate, the plate will go down. Maybe there are some springs here. And the plate will go down. So what we can do is to have some piezoresistive material. Maybe if we focus on that side here, there is the plate. There is a carrier. And if the plate goes down, then the carrier will be bent. And this bending of the carrier, that's what we are measuring. That's like if you're buying a scale for you, and it's the same principle. So if we focus on that carrier that gets bent, then there is on one side of the carrier, there is a piezo resistive resistor, or let's say material, and that is our sensor. We put one sensor on top of the carrier, and we put another sensor on the bottom of the carrier. So this one will be comprimated, the other one will be extracted. Top sensor will be stretched. So because of the problem with piezoresistive materials, so they change their resistance based on mechanical stress, but you cannot use only one resistor because the piezoresistive material changes its resistance with temperature. So if you use only one, then you can't do a temperature measurement, but not the measurement of the mechanical stress. So you need to use a second one to compensate the temperature changes. This is very important, but we will focus on that when we are doing these measurement principles. For today I will give you only the idea what can be done and what consists
What's the name
on a sensoric.
The name of this piece of
Piezoresistive material. In English. There is no other name. In German it's called Denmeschstreifen. In German it's called Dehnmessstreifen. But in English it's called piezoresistive material. Based on mechanical stress, these sensors change their resistance. Yeah? If you stretch them, then the resistance gets higher. It's not that it's changed from 100 ohms to 1 kilo ohms. It changes maybe by 1 or 2%. Yeah? So that's why you have always to use 2 of them to compensate for temperature.
Also die Piezo itself is a sensor material.
The piezo, this is more or less a small, like a tape, you can put on the carrier, and on the tape there is a small, it's like a chip, there is a small resistive layer, and that's the piezo resistive material. But nevertheless, you have it with every wire. If you stretch the wire, then you increase the resistance of the wire. So that's another way weighing the vehicles. But this is not very user-friendly on the highway, because if you're traveling, you have to be very slow crossing this weighing system. So are there any other ideas for detecting the cars here?
With temperature?
Temperature has to do. We can detect the environmental conditions. This temperature is one of the most important, so we definitely will focus on temperature measurement. But for detecting a vehicle,
a inductive strings, like a ball, which each vehicle which pass through that, for example, ball, send the air to the sensor. So
tubes. Okay. That would be also a possibility. You can have maybe a tube, and here you use some pressure sensors, and if the vehicle is going across the tube, then the air within the tubes will be pressed here, and you can measure here a higher pressure. Maybe here you can make a stop. So if you're traveling, if the car is passing this tube first and then that tube, you know that the car is traveling in that direction. But tubes, it's not very fail-safe.
But because if there is another car coming from the other direction,
yeah, then on the other side you have another tube. Another tube here, with some sensors here and here and here and here, and here also a stop in between. But it's a very mechanical sensitive system. You can imagine if there are 1,000 cars running across the tube, then the tube is flat and
nothing changed.
Nothing will change.
But what is the target from detecting the number of cars, or what we need?
The number of cars, the number of cars, how many cars will pass. Maybe there is an area with an hospital, you won't keep it calm, so you want to measure how many cars, or you're deciding to build a highway that is going around that city.
The capacity.
So you want to check the capacity on that street or whatever.
So why not using the speed as a for the sensor?
How do you detect the speed?
Yeah, what I'm thinking is for a simple sensor, because I used it once only. Yeah. That when the sensor sent an infrared, and then when a car pass or anything pass, cut that line between.
That's a light fence.
Yeah. I don't know the name exactly.
You can also implement a light fence. Maybe you use some laser diode or laser on that side. Have a mirror on the other side.
Yes.
Reflect it back and got a detector here. Mm-hmm. That's what we call a light fence. Mm-hmm. So if the car is passing here, then the beam get interrupted and you have a detection.
Yeah.
But the problem is you cannot separate between these two directions. Huh?
But
So
we
if
can.
the car is passing here or here, but you can put the mirror in between.
Yeah.
But normally we don't like to have something in the middle of the street.
But you could detect the direction by sending impulses and measure the time of the...
This is a radar principle, a radar sensor. This we can also talk about a little bit. So a radar sensor you know these side boxes on the street. What is going on here? It emits an electromagnetic wave in the area of 60 or 70 gigahertz, something around that, 50 to 70 gigahertz. And if a car is coming here, then this beam is reflected maybe from the front grille, from the windscreen. The windscreen is not so good because the reflection will go straight up. So it's better to have the reflection from the grille. And the electromagnetic wave is reflected back to the radar device and will be detected. So with this setup, you can not only detect the attendance of the car, you can also detect how far is the car away and how fast is the car moving. So how can you detect how far is the car away?
From the time of returning
It's time
of
of flight. This is what they call time of flight. Detection. So the electromagnetic wave is more or less traveling with the speed of light. So it's with C0. It's 300,000 kilometers per second. So out of the time, you get the distance. What you have to care is that the wave has to travel double the distance. It travels to the car, gets reflected, and comes back. So out of the time of flight, this is in the area of some nanoseconds. So it's not seconds, it's nanoseconds. You can calculate the distance to the car.
and the speed also
And the speed.
in another reading when we read in another time.
This is one option. You can check another reading, then compare the distances. Or, what else do we got? Can we do it with one pulse?
With
Or
one pulse, I think. So.
detection?
You can check how the outsending wave is changed with the Doppler effect.
The direction.
That the difference between.
Doppler, yeah.
If the car
An
will...
Austrian physicist, Christian Doppler, and his findings was that if you got a moving target, let's say that the wave is exactly 60 gigahertz. I'll give you the details here. Say we use a fixed frequency radar source. So this is the radar source. And we use 60 gigahertz. And we got a non-moving target. So it's a fixed target. Then the reflected beam will also show you 60 gigahertz. But now if the target is moving, and if the target is moving towards your radar source, then the frequency gets
higher, yeah.
higher. Yeah? That's the same with an acoustic beam. So if the target is moving, you might read 60.05 gigahertz. No? So the frequency shift is directly related to the speed of the target. That is what normally the police is using. So there's only one shot, and they can measure also the speed. So if the target is moving towards your radar source, then the frequency is increased. The actually equation you can take out of the physics book. It's also how we do in astronomy measure the speed of the planets surrounding the central star. And it's called the Doppler effect. Doppler effect. Yeah?
And if the car will move away from the detector,
If the car is moving away,
So
then
they
we'll
are-
have a lower readings, 59.995 gigahertz. Yeah?
So,
And this you can use with electromagnetic waves, or another sensor principle is based on ultrasonic waves. Maybe you have it in the cars for checking the distance during your parking maneuver, checking the distance to the sideboard or the next car. There you can use ultrasonic waves. Because if you're doing that with electromagnetic waves, then the time gets so small that you cannot exactly measure the time span of the echo. So then you use ultrasonic waves in the area of 40 to 50 kilohertz. So I'm not allowed to move. Huh?
no problem.
Okay, that's another way. We can use radar sensors. But as I said before, a radar sensor is an active sensor, so you have to actively transmit some electromagnetic waves into the scenario and to watch for a reflected wave or an echo. But nevertheless, very often radar sensors are used, especially for new automatic driving mechanisms, maybe to detect the distance to the car in front of you. Here we use radar sensors. Huh?
Well, I think there is another.
Also for detecting bicyclists and also pedestrians.
Yeah.
Because this is
Any
one of
object, I think.
the few sensors we can use for detecting pedestrians.
Another should be monitoring, as you mentioned.
That was image processing.
Process by, for example, using at the intersections or below the bridge or something.
Yeah.
I think
This is CCTV cameras where you can detect the pedestrians or if there's a lorry on the street or some critical section of
Is
the
it
road.
kind of intelligent sensors or?
Not really. The image processing software might be intelligent, but normally it's done by an operator. Yeah.
Why we don't use the vibration to detect the vehicles?
We can use that, yeah? So it's another way. Our sensor, we can use a small sensor here, a vibration sensor. Which is also a good option, yeah? What we are looking here for are small sensors and without the overhead of a risk machine with millions or hundreds of nips to get our results. What we are looking is a physical principle so that we can easily detect our vehicle. So a vibration sensor will be a good idea. Vibration sensors are also based on piezo-magnetic or piezo-resistive materials. So a vibration sensor, this is just a resistive sensor. A resistor based on a piezo-resistive effects. stop anyway. Sorry. So here we can use, excuse me, piezoresistive materials, and the vibration, we have to monitor the vibration. So maybe if there is a, we put it along our road section, and if a lorry is traveling by our sensor, normally the output of the sensor is quite quiet. And if the lorry is traveling by, we will see every axle. So every axle that is traveling across the sensor will give us a typical vibration pattern. So this we will feed to a digital signal processor, and then we can analyze the vibration pattern. So what we're interested in are these sections here in our output signal. So we can check each axle. So we can say it's a lorry or it's just a passenger car. And the magnitude of our spikes is proportional to the weight of the...
The speed doesn't make any difference.
What, sorry?
The speed doesn't make any... Because
the
I
speed
think...
is covered in the frequency here. But not always. If you got it in the area a typical frequency or a resonant frequency, then the frequency is not changed.
If we have congestion, we have problem with this.
With congestions, you will have problems because the car is really moving very slow.
You can
the
take
vibration pattern will be very small.
And maybe if it is fully saturated and the car should be stopped on the sensors, nothing happen. But
if you're detecting a stop, then it's not possible with the vibration.
But I also told there is a vibration if even the car is stopped.
Yeah, but that's the output of the sensor will then very small. And then it's hard to distinguish the car from the noise, because you have all the time noise on your output signal. So it's not really a flat line. We will cover noise in 1 or 2 lectures. So you always have some noise on your output signal. And then if the signal you're looking for is maybe double the noise, then you can detect it. But if the output signal is trained in the noise, you cannot detect it. Because there is no ideal sensor. So every sensor will give you noise, depends on the physical principle, how much noise you will have, but you can be sure there will be some noise, and if the noise is higher than your output signal, then you cannot detect it. But vibration sensor on the highway, it's a good idea. Huh? And
But
also, what else could we use?
But
Vibration?
I'm sorry for the same vibration. The problem I think if there is an earthquake, for example, Earth is moving.
Yeah.
So there will be a
Then
big
you will have a big peak.
even if there is no
But
cars.
it's not that common that we have earthquakes here, so we can
Use it.
deal with that. So if there is an earthquake, maybe our traffic chaos is the least problem of all. So the earthquakes shouldn't be the problem, but also you can detect earthquakes with this kind of sensors. So there's another application for that kind of sensors. Any other idea?
I know
What kind of physical?
of a similar project, but not using vibration, but using acoustic sensors in Great Britain.
Acoustic sensors, yeah. There is closed related to vibration. We can use an acoustic sensor, a microphone, for example. It's done in the Kaisermühlentunnel. They put there some acoustic sensors to monitor the traffic flow. You have a telecom lecture with Mr. Kastner, and you can ask him about acoustic sensors. He's a specialist on that. But what we're doing is, maybe we have the tunnel, And we would like to monitor the cars that are running through the tunnel, and every car can be seen as an acoustic source. The main sources are the running of the tires on the street. So that's the main source of noise here. And the noise is primarily a wideband noise. So it's starting from 5 Hz up to 100 kHz, depending on the speed of the car. And this noise is monitored with some microphones on top of the tunnel. And all the microphones are linked to maybe a digital signal processor. So they link together, DSP. The next microphone. So the source is traveling from one microphone to the next microphone. So what can you easily do is to check the direction of the movement and also the speed of the movement. Because if we are monitoring this one here, if the car is under the microphone, we will have a peak in our noise amplitude. If we are checking the next, this is the first. The second sensor will have the same peak, but a little bit later. And out of this time shift, you can
Measure the speed.
estimate the speed of the car.
You mean each car has emitted some noise?
Each car is more or less a noise source. The noise is traveling. And if you got a noise source, then the intensity compared to the distance will drop with 1 over squared r. That means the further you get from the center of the noise source, the lower the intensity will get.
And also we have other source of noise in the tunnels.
Yeah.
Turbo motors for changing
The bands.
yeah.
Yeah. But these are normally not that loud like the cars. So get into the Kaisermühlen tunnel and check if you can hear the bands. If they're running full speed, then you may maybe hear them, but the noise spectrum is quite different. So the cars have a characteristic sound, and it's a noise spectrum.
But I think it will be very hard to distinguish special cars if there is more traffic or something. So
That's one main problem. If there is heavy traffic, then this will also fail. Huh? So you see, with every sensor you get some specific advantage and some drawbacks. So that's what you should learn here.
Combination.
You cannot use the same sensor for every problem. Yeah? So for every problem, there you have to use some other sensors. And sometimes you have to use maybe 2 or 3 sensors.
Different types.
Different types, different physical principles to solve your problem. And that's what we call sensor fusion. Maybe if you use a vibration sensor, an acoustic sensor, a magnetic sensor, you collect all the outputs of the sensor and you generate one main output. That's what we call sensor fusion. And very often this is done, yeah? But nevertheless, remember back to our first sensor, detecting the magnetic field changes. You do not have problems with other cars. You do not have problems with environmental conditions. So it's very fine sensor principles. It's a passive sensor. The magnetic field is already here. Yeah? So you do not have to generate the stimulus, but it's not very common.
Why can't we use the resistance of the car
The
as a sensor?
resistance of the car.
Yeah, in
How would you
yeah,
like to
big-
measure the resistance of
yeah,
the car?
it will. We will have to use the electric current, but
This you can do, yeah?
yeah, but we
Yeah, you
will.
can also use a magnetic sensor. The main problem with magnetic sensors might be an underground running under your street, because the underground is creating a heavy magnetic field because of the current tracks.
Yeah, but I'm talking about the resistance of for the electricity
Yeah.
as a circuit. Like we create a circuit, and if the car moves or any vehicle moves, the resistance on that circuit will increase. I don't know. I can't explain the idea.
But you have in one semester you have the ITS project. There you can develop your own idea of the sensor or sensor system, whatever. So there's
But it
plenty
will-
of time to develop your own ideas.
Okay.
But now I don't understand what you're meaning by the resistance of the car, because the car is made out of tin. The resistance is very low. But what you can do is a capacitive sensor. That will work. Yeah?
Okay.
But resistance,
It's not a good idea.
maybe you got a good idea, but I've never heard about it a lot.
I think you can also try to detect emissions from the car in sort of Bluetooth or smartphones or so on.
This you can also do if there is a smartphone in the car. You can detect the Bluetooth radiation or something like that. But this is heavily depending on the
Driver.
infrastructure in the car. Because if they don't carry any smartphone or whatever, then you cannot detect it.
But in future with the e-car, it should be
Yeah.
getting standard.
But that might be in 50 years, huh? Or something like that.
Maybe, I don't think it will work very fine, but especially in tunnels, you could also measure the air pressure for an incoming car.
This you can also do. You have a microphone and maybe a pressure sensor, and you know that from the underground, when the underground is running into the station, you have a pressure wave in front of the underground. But this is normally not done for cars, because cars are too small compared to the cross section of the tunnel, so that you don't have a real pressure wave in front of the car.
And another problem is another bound. I mean, one comes from this way, another comes from that way.
Yeah,
so
yeah. This is only working for undergrounds, because the underground train is more or less filling the whole cross section of the tunnel, and then the underground drags the whole air in front of it.
And we can use some light sensors and reflexive changes in the movement of place, and it's more useful for the dark hours of the day and night. And another thing, we can use some rays. For example, with gamma rays, we can understand some object which is go forward or backward.
Yeah,
In the change of the color of red or blue.
yeah, yeah.
Function.
But the problems with gamma ray is that you will instantly kill every
Someone in the car.
passenger on the car.
We can understand this.
Yeah. So
Well, at least we detected
gamma,
something.
gamma ray is not a
That's
good
the-
idea, because it will kill everyone getting close to the source. Eh?
We're doing the target.
But you can use it during dark hours, that's true. Yeah? Never, you don't need sunlight to kill the people.
The only problem.
So, any other ideas? Or do you think we have covered all the possibilities?
There is more.
We covered a lot.
Temperature.
Temperature, yeah, but temperature, a car doesn't change the temperature in the surrounding area, hopefully. You can easily detect the burning car, but we would like to detect normally running cars.
Can we detect the cars with the chemical changes?
You can detect the exhaust gases.
Yeah, that's what I'm
But
saying.
this will be tricky, to say the least, because if the car is traveling very fast, then the exhaust gases get distributed all over the area. So that's also not possible.
But what will work at bad weather as well is the infrared detection.
Infrared detection, yeah, but it's more or less also the same like a radar.
With
Or do you mean the passive infrared detection from the...
you can measure with photodiodes, for example.
Yeah. This you can do, a passive infrared sensor. But this is normally done for pedestrians, or if you come into a room and the light goes on. This is the classical application for a passive infrared sensor. Because if you're a traveling car and if there is only one person in the car, the one person doesn't emit so much infrared.
The motor.
The motor, yeah, but if you just have started the car and you're running through this section, then you won't get detected. But it's an option, yeah? So we also have to keep in mind passive infrared sensors. So you see there is a whole bunch of different sensors, different sensor technologies, and what you have to do is to pick out the right one for your application. Yeah? That's the tricky thing with Sensorics. So there's not just one or two ways to do it, there is a magnitude of different ways, and every way has its advantage and drawback. And this you have to scale down if this can work. So we have the idea what kind of different technologies we can use, and now we focus a little bit on the sensor itself, and we will discuss what different kind of functional sections will make up a sensor. So in general, what is the duty of our sensor? The sensor is normally also called a transducer. And the use of such a transducer is to convert one physical quality to another physical quality. Most of the time we have here a physical quality, maybe like air pressure or temperature, maybe pressure, temperature, or noise, whatever. That's an acoustic wave. And the goal of the transducer is to give us an electrical quality on the other side. So we are not interested in transducer that transform maybe pressure to temperature. Because with temperature we have to use the next transducer. Because we are doing electronics in Sensorics, so the output quality must be an electrical one. That might be resistance, that might be capacitance, that might be a frequency, that might be a time, or maybe also some digital code. That's very common nowadays. So if you're talking about the acceleration sensor or something like that, sometimes they will give you a binary code. That's the easiest one. You can directly interface to your microprocessor. So that's more or less the goal of our transducers.
So transfer the physical
It transfers one physical quality
to an electrical
another,
Yeah.
and the other physical quality should be an electrical one. Eh?
Yeah. How?
What is R?
Resistance. No.
R is resistance.
And what means FS?
Frequency.
Maybe sampling frequency, or let's put it as away, so frequency just. So one example, maybe we use our acoustic sensor. So everyone knows what's taken to set up an acoustic sensor. It's also known as a microphone. And I suppose everyone knows how a microphone is working. So an acoustic sensor. Also known as microphone. That's your device has an acoustic sensor as well as an So, what's a microphone? How is it set up? Any ideas what is going on here? What is the physical input quality to our microphone?
No idea.
Air pressure. Air pressure is not quite enough.
With several frequencies, the change of the pressure.
The change of air pressure. Because when I'm talking to you, it's not an increase in air pressure, because this you cannot hear. If we seal the room and increase the pressure by 1%, then everyone gets a blown ear, but you won't hear it. So let's think about this, what is really changing. And everyone got two acoustic sensors integrated into our head. So what we are hearing? Any idea?
The vibration.
How much pressure change do we
I thought it's something with the
Yes.
vibration, with the
that we
frequency.
can hear it?
It's something. I thought it's something with the vibration and frequency of the voice, because we can hear only.
Yeah. So when you speak to me, you got local changes in air pressure,
Yeah.
but how much does the pressure change?
The air pressure, the normal air pressure is 1 bar, I think, right?
It's roughly around 1 bar.
So I don't think there is something that changing.
Yeah, there are some
Detectors
changes.
on our ears are really sensitive to, vibrate by the air pressures which caused by the others, sources,
Yeah.
like for example
Yeah.
speaking.
So let's boil it down to a scale. So we got the air pressure. You said it's roughly around 1 bar. It's 1.013 bars during good weather conditions. And this is changing with the weather condition. So if we got bad weather, we roughly have around 990 millibars, so 0.99 bars. So it's changing not that much, but a little. And what do you think, how much do we have to change the air pressure so that we can hear it?
Very low.
Very low. We don't talk about frequency, this we do afterwards. But normally we have a static air pressure. So here in the room we have a static air pressure of roughly 1.013 bars. So if I'm talking to you, then this static air pressure is changed a little bit. Huh? So how much do you think is the change in air pressure so that you can understand me?
Half of the static.
Some decibels.
20 hertz.
20 hertz. Huh? Half of it. We're here. So here we get the vacuum level. It's 0 bars. You say half?
1 millibar.
1 millibar. So 1,000th. So let's say delta P is 1 millibar. Any other ideas? So what is it? The bar is not the SI unit. What is the SI unit for pressure?
Pascal?
Pascal, yeah? So how many Pascal is 1 bar? 1 hecto, what is 1 hectopascal?